Model-based systems engineering was designed to eliminate document-centric chaos. Instead, it often replaced paperwork with an unmanageable web of graphical gridlock. The root of this problem was structural. SysML version 1 was built as an extension of the unified modeling language. This architecture forced engineers to rely heavily on visual diagrams to define every relationship within a system. This block definition diagram shows the liability this created for traceability. Proving a component met a specific requirement meant manually drawing literally dashed lines across complex canvases. As systems scaled, these models devolved into visual spaghetti. The underlying engineering data remained locked inside proprietary software interfaces. SysML v2 is a complete architectural teardown of the language. At the core of this rewrite is KerML, or the kernel modeling language. KerML severs SysML's historical dependency on UML. By removing the requirement for graphical boxes, KML introduces a declarative foundation built directly on first-order logic. This enables the central operating principle of SysML v2, model as code. System relationships are no longer visual artifacts. They are first-class textual syntax. To see how this works in practice, we will build an executable digital thread from the ground up, starting with a single abstract requirement. This architecture moves systems engineering towards writing mathematically verifiable constraints rather than drawing passive pictures in closed tools. We are going to construct a verifiable system component, starting entirely from an abstract system requirement. In SysML v2, requirements no longer exist as static graphical text boxes. They are formal code definitions. To establish a strict parent-child logical hierarchy, engineers use the derive keyword directly inside the code block. Declaring these dependencies in text eliminates the need for the manual derive requirement arrows that previously cluttered the canvas. Next, we use the refine keyword. This maps a specific requirement directly to a system behavior or use case, entirely within the text block. Because this declaration happens locally within the requirement's code, you can understand the system's intent without cross-referencing a separate mapping diagram. Hierarchical complexity is managed through semantic syntax, removing the need for physical mouse manipulation to establish traceability. With our abstract requirements defined, we move to the physical structure of the system. For this scenario, the system architecture must adhere to a strict vehicle weight limit of less than 1,500 kilograms. This code block shows a part definition, or part def. It represents physical components like the chassis and engine, each with assigned mass values. We type the satisfy keyword directly inside this physical component's part definition block. By placing satisfy inside the part definition, the design decision becomes a native internal property of the component itself. Because KerML is logic-based, the 1,500 kilogram limit is processed as an executable mathematical constraint rather than a simple text description. The model execution engine calculates this physical compliance in the background automatically as attribute values change. By embedding this relationship in the code, the model proves its own physical compliance. Engineers no longer need to rely on external spreadsheets for these calculations. Now we move to actively verifying that the vehicle weight constraint holds up. In traditional MBSE, verification was often just a static test case icon pointing to a requirement on a diagram. The SysML v2 verification case is a dynamic test scenario that lives natively inside the model. It contains a specific subject, objective, and action sequence. The verify keyword formally maps this executable mathematical action sequence directly back to the target requirement. Capturing the rationale behind these design decisions is the next step in the process. SysML v2 replaces disjointed graphical rationale notes with direct textual integration. Engineers use inline doc blocks and structured rationale metadata tags, placing them next to the relevant verification code. Verification and system rationale are now active, fully executable logic, residing perfectly synchronized with the core design data. This shift toward code-based modeling changes the macro-level systems engineering workflow. Because the model is text, SysML v2 files can be stored, branched, and compared in standard version control systems like Git. Pushing a model update to a repository can now automatically trigger a continuous integration and continuous deployment, or CI/CD, pipeline. This liberates engineering data from proprietary software interfaces and manual relationship matrices. Using REST and OSLC APIs, engineers achieve true API-driven decoupling. Python scripts can programmatically query the model for automated coverage analysis, bypassing modeling software entirely. If a requirement is modified, the script instantly outputs every structural block and test case affected globally. This programmatic extraction ensures that requirements management tools and system design tools operate together as a single source of truth. The combination of KML constraints, Git versioning, and REST APIs delivers a real-time digital thread. SysML v2 moves the discipline away from manual diagramming and toward a framework of verifiable logic. While a diagram provides a snapshot, this executable code serves as the authoritative source of truth.